Welcome. In the world of computer-aided design or CAD, we often focus on the visual aspects, the lines, shapes, and assemblies that create a digital prototype. However, the true power of modern CAD lies in its ability to embed deep, quantitative data within these drawings. Today, we are diving into a crucial set of tools that unlock this data: inquiry commands. Specifically, we'll be exploring the area, distance, and mass properties commands. These are not just simple measurement tools, they are analytical instruments that enhance the entire design workflow, providing precise information that complements traditional documentation methods like annotations, dimensions, and hatching. Whether you're working in AutoCAD for 2D drafting, SolidWorks for mechanical design, or Revit for architectural modeling, these commands are fundamental. They transform a simple drawing into an intelligent model, allowing us to ask critical questions about our design. How much surface area needs to be painted? What is the precise clearance between two moving parts? What is the total weight and center of gravity of this assembly? By the end of this presentation, you will understand how these commands provide the essential data needed for accurate documentation, efficient revisions, and informed engineering decisions, forming the backbone of modern, data-driven design. Before we delve into the inquiry commands themselves, it's essential to understand the foundational context in which they operate. A CAD model is a rich tapestry of information, and its language is spoken through annotations and dimensions. Annotations are the notes and symbols that communicate the designer's intent. This includes everything from material specifications and finish requirements to assembly instructions, often using multi-leaders to point to specific features. They ensure that anyone viewing the drawing understands the why behind the geometry. Dimensions, on the other hand, define the what, the precise, measurable geometry of the model. But they are far more than just static numbers. In modern CAD, dimensions are often associative and parametric, meaning they are intelligent links that control the model's shape. If you change a dimension from 50 mm to 60 mm, the model updates automatically. This system includes critical information like tolerances, which define the acceptable range of variation for a given measurement. All of this is governed by international standards like ISO and ANSI to ensure clarity and consistency across industries. This rich layer of information sets the stage for our inquiry commands, which we use to verify and analyze the data established by these fundamental elements. Another key visual element that provides context in CAD drawings is hatching. When we create a section view, essentially a virtual slice through a 3D object to see its internal structure, we need a way to represent the material that has been cut. This is the role of hatching. It fills the enclosed area of the section with a specific pattern that signifies a particular material based on industry standards. For example, a pattern of evenly spaced diagonal lines might represent steel, while a different pattern could signify aluminum, concrete, or wood. This visual shorthand is incredibly effective for communicating the internal composition of an assembly at a glance. Just like dimensions, modern hatching is associative. This means it is intelligently linked to the boundary that contains it. If you modify the shape of the object, the hatched area automatically updates to fill the new boundary. You can also adjust its properties such as the pattern itself, its scale, and its transparency to achieve the perfect level of clarity in your drawings. Hatching therefore works in concert with annotations and dimensions to create a comprehensive and easily understandable technical document which can then be further analyzed with our inquiry commands. Now we move to our first inquiry command, area. At its core, area command is designed to calculate the exact size of an enclosed 2D region. By simply selecting a closed boundary or clicking points to define one, the software instantly returns not only the total area but often the perimeter as well. While this may sound simple, its applications are vast and critical across numerous industries. For an architect or interior designer, the area command is used daily to calculate the square footage of rooms for flooring estimates, paint requirements, or HVAC load calculations. A civil engineer uses it to determine the acreage of a parcel of land from a survey drawing. In manufacturing, it can be used to calculate the surface area of a part that needs to be coated or plated. The power of this command lies in its speed and absolute accuracy. It eliminates the tedious and error-prone process of breaking down complex shapes into simple rectangles and triangles for manual calculation. The area command ensures that material orders are precise, reducing waste and controlling costs, making it a fundamental tool for planning and estimation.
Our next tool, the distance command, is the digital equivalent of a high-precision tape measure and caliper set. Its function is to measure the precise spatial relationship between elements in your model. This isn't just about finding the length of a single line. The distance command can determine the shortest distance between two complex curves, the clearance between two parallel surfaces, the angle between non-parallel lines, or the x, y, and z coordinates of any point. Its primary role is in validation and verification. An automotive engineer might use it to check the clearance between a spinning fan blade and its housing, ensuring they will never collide. A product designer can verify that the gap between two mating plastic parts is correct for a perfect snap fit. In large-scale construction, it can be used to check the alignment of structural steel beams in a 3D model before they are ever erected on site. The distance command is an essential quality control tool. It allows designers to interrogate their models, ask specific geometric questions, and receive instant accurate answers, ensuring that every component fits and functions exactly as intended. We now arrive at the most powerful of the inquiry commands, mass properties. This tool takes us beyond simple geometric measurement and into the realm of true engineering analysis. The mass properties command analyzes a 3D solid model and extracts a wealth of physical characteristics, but there's a critical prerequisite. You must first assign a material to the object. By telling the software whether the part is made of aluminum, ABS plastic, or titanium, you provide the crucial density value. With this information, the command performs a series of complex calculations instantly. It will tell you the model's total volume and surface area. More importantly, it calculates the total mass or weight. It pinpoints the exact location of the centroid or center of gravity, which is vital for understanding balance and stability in any design. Furthermore, it determines the moments of inertia, which describe how the object will resist rotational motion and are fundamental for any kind of dynamic analysis like stress or motion simulations. The mass properties command provides the raw data that underpins almost all advanced computer-aided engineering, transforming a 3D shape into a virtual physical prototype. It's crucial to understand that these inquiry commands do not operate in isolation. Their true power is realized through a seamless integration into a structured and intelligent CAD workflow. Think of a design built on a foundation of well-organized layers, controlled by powerful parametric dimensions and defined by precise geometric dimensioning and tolerancing, or GD&T. In this environment, the inquiry commands serve as the validation and feedback system. After you make a parametric change to a model, you use the distance command to verify that your critical clearances are still within specification. After finalizing a complex housing, you use the mass properties command to ensure its weight is under the target limit. You use the area command to get the data you need to create an accurate note for the total surface to be painted. This creates a powerful feedback loop. The design elements, dimensions, tolerances, geometry define the model, while the inquiry commands, area, distance, mass properties allow you to check, analyze, and extract data from that model. This synergy transforms a static drawing into a living, interconnected digital prototype, where revisions are efficient and data is always accurate and accessible. In conclusion, the inquiry commands for area, distance, and mass properties are indispensable tools in the modern engineer's and designer's toolkit. They are the instruments that elevate a CAD model from a mere picture to a profound source of data and intelligence. By providing instant access to precise quantitative information, they ensure that all documentation derived from the model is impeccably accurate and reliable. This capability dramatically streamlines the design process, allowing for rapid iterations and efficient revisions, as designers can immediately validate the impact of their changes. The data extracted is not just for documentation, it serves as the essential foundation for more advanced engineering analysis, from finite element analysis to complex motion studies. Ultimately, this leads to better, more informed and highly cost-effective decision-making. Whether it's optimizing material usage based on an area calculation, preventing costly assembly failures by verifying a critical distance, or balancing a rotating component using its center of gravity, these commands empower us to design with confidence, innovate faster, and build a more efficient and reliable world.